Okay, so in this section, we're going to go from discrete random variables to continuous random variables, because not necessarily every single time is it going to be just a value where your value is going to be very distinct numbers, such as 0, 1, 2, 3, or 4. Well, what happens whenever we have 1.5, 1.27, and they're not discrete numbers? Well, we're going to take a look at what the probabilities look like if your variable or your value is not just discrete, but it's continuous. Think of more of like a ruler. So discrete random variables commonly arise from the situations that involve counting something. However, situations that involve measuring something often result in a continuous random variable. And actually, when we go through this part of the unit, this is actually something you've already done before. You've seen continuous random variables before, and we'll take a look at that in a minute and see what that looks like. What is the difference between a continuous and a discrete random variable? A continuous random variable takes on all the values in an interval of numbers. So instead of just separating it from 0 to 1, it would be everything between 0 and 1. The probability distribution of x for a continuous random variable is described by a density curve. So this is pretty much the approximately normal curve that we've talked about in our previous sections. The probability of any event is the area under the curve. So just remember in the previous sections when we took a look at our approximately normal curve, we would always say the probability of something occurring, it was an interval under the density curve that we looked at. So basically we're just going to go back to our normal curve and find probabilities using our normal curve. So the probability model of a discrete random variable x assigns the probability between 0 and 1 to each possible value of x. So for a discrete random variable, we have our table, we have our possible values of x, and then we have the probabilities that add up to 1 in our table. With a continuous random variable y, it has infinitely many possible values or infinitely many probabilities. So all continuous probability models assign a probability of 0 to every individual outcome. Only intervals of value have positive probability. So just remember back when we did normal curves, we couldn't ever find the probability of one event occurring. It always had to be an interval. Since the probability is an area under the curve, we can't say that the area is basically just x equals 10. That would just be a height. It would have no width. So to get a width, we have to have an interval of values. All right, so let's just take a look at the difference quickly between a continuous random variable and a discrete random variable. With discrete, let's say we want to select a digit between 0 and 9. So each digit between 0 and 9 has a 1/10 chance of being chosen. We can assign each digit separately. It's like counting them 0, 1, 2, 3, 4, 5, all the way up to 9, a probability of 1 over 10. That's easy to make in a table. Rolling a dice is the same way. What's the probability of rolling a 1 through 6? I can separate those 1, 2, 3, 4, 5, 6. They each have a 1/6 chance of occurring. So in basketball, basically, what's the probability of making 1, 2, or 3 shots during a game? So the only possibilities are making 1, 2, or 3. I can write the probability of each of those underneath the probabilities in the table. However, a continuous is, what if we want the probability between 0.3 and 0.7? We cannot assign probabilities to each individual value of y, okay, and then add them up because there's infinitely probabilities. So between 0.3 and 0.7 is 0.31, 0.32. We can't assign probabilities to each of those, so that's why we represent this using a density curve. So with a continuous random variable, we can't make a table because I can't make a table with every single probability on it, so we make a density curve. Just keep in mind that you always have to have an interval of values. What's the probability that x is equal to 0? Well, that's a height here, but it's no width, so that doesn't make sense. I have to have a width in order to get the probability or this specific area under the curve. Okay, so if x is a continuous random variable, this goes along with what we were just talking about. What does the probability that x is greater than a, how does that compare to the probability that x is greater than or equal to a? So let's say, what's the probability that x is greater than 1? That would be all this area to the right or 1. How is that different than the probability that x is greater than or equal to 1? So starting at 1, the area to the right of 1. Since there's no area at x equals a or x equals 1, that's just a height, then with a continuous random variable, the probability that x is greater than a or x is greater than 1 is the same as the probability that x is greater than or equal to 1. All right, so they're the same probabilities because at that single point of 1, there's no width, so I can't find that area or that probability. Okay, so Going back to our normal distribution questions with a continuous random variable, we're just basically sort of giving it a different name here. This is going to be what you did before. So the heights of young women closely follow the normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. We're choosing one young woman at random. Call her height y. So now we've defined what y is. That's our random variable is y, the height of a randomly chosen woman. If we repeat the random choice many, many times, so if I choose one young woman at random many, many, many times, the distribution of values of y is the same as the normal distribution that describes the heights of all young women. So it's basically like saying if I'm taking a sample over and over and over and over and over and over and over again and put all of those heights into a curve, the heights of that of all of my samples follow the same as the population of heights of all young women. So we want to know what's the probability that the chosen woman is between 68 and 70 inches. So what's this probability? Well, we know how to do this. This is just using our z-scores in our calculator. So this is the same six-step process that we used before. So make sure you define your distribution. We're looking at y as our randomly chosen young woman. That's our random variable here, approximately normally distributed with a height of 64 inches and a mean of 2.7. Okay, so make sure you include that. State the probability you want. You want the probability that's between 68 and 70. And remember, it doesn't matter if you write 68 less than or equal to or less than, since the equal to sign doesn't make a difference in a continuous random variable. All right, so we have our picture that we drew representing the area under the curve between 68 and 70. I have the z-scores of both 68 and 70. Make sure you show the work for both of those. And then remember, once you have the work for the z-scores, you can just show this probability statement with the z-score and then get the answer from your graphing calculator of 0.0562. Okay, so the probability that we choose one woman at random and her height is between 68 and 70 inches is either 5.62% or 0.0562. Okay, so why don't you go ahead and take a minute and try this question and check your answers on the next slide. So this is very similar. We're just taking a look at weights of 3-year-old females. Okay, so let's take a look at A, B, and C. C is probably the trickiest one, but find the probability that the randomly selected 3-year-old weighs at least 30 pounds. So that's 30 or more pounds. Now, since it says at least 30 pounds, include that greater than or equal to here, just to show that you're following the directions in the question, even though it doesn't make a difference whether or not you have it underneath there for your calculation purposes. But for the purposes of people reading your work to make sure it matches the question, include that greater than or equal to. All right, number one, we have our defining our distribution. It's normal, mean of 30.7, standard deviation 3.6. What's the probability statement? Okay, greater than or equal to 30. Your z-score is negative 0.19. Probability Z is greater than or equal to that, and then your final answer. So there's about a 57.71 chance that a randomly selected 3-year-old will weigh at least 30 pounds. Okay, so the second one is the same that we had discussed on the very first question. So probability that's between 25 and 35. Now, once again, if you define this distribution to be approximately normal at the very beginning of the problem, you don't need to do it each time. But here, I'm just showing that to you. Now, notice this probability statement is different between 25 and 35. Well, there's no less than or equal to sign here. Why? Well, between 25 and 35 is not inclusive, so we're just making sure that our work follows the problem, so I'm not going to include that less than or equal to sign. I have the z-score for each of them, the data value minus the mean divided by the standard deviation, data value minus mean divided by the standard deviation, and then here's your probability statement with your z-scores, okay? And then you can just use your graphing calculator to get that 82.59%. So there's an 82.59% chance that a randomly selected 3-year-old weighs between 25 and 35 pounds. Okay, so this one was a little bit tricky. So if we know that the probability that x is less than k is 0.8, find the value of k. So we're working backwards here. We actually know the area under the curve. but we don't know what the data value is. So remember, if I do inverse norm of 0.8, if I'm going to draw a curve, okay, so just as a refresher here, um, if this is K, the area less than that is equal to 0.8. Okay, so remember that if we're talking about the area less than that, that's what your calculator always finds, is your calculator always finds the area less than or equal to that specific number. Okay, so then what we did is we're doing inverse norm of 0.8, so that means 0.8416, that's going to be your z-score. So we plug it into our formula. Our z-score is equal to the data point minus the mean divided by the standard deviation, do the math, and you get 33.73 pounds. Okay, and just keep in mind though, if this had said greater than 0.8, that would be the area to the right. But remember, in order to do that, you'd have to, your calculator always does the area to the left of the 8. So if you say inverse norm of 0.8, that's always the area to the left. So just keep in mind that you're typing the right thing in your calculator whenever you are finding your correct area, or your correct z-score from a given area. All right, so in this section, what did we do? Let's just do a quick summary. We talked about the probability distribution of a discrete random variable. We talked about the mean, or the expected value, and what that is, okay? Remember that the expected value is after many, many, many runs of a trial. What can we expect to get? The standard deviation is after many, many, many trials. How far away on average are we from the expected value or the mean? And then we computed probabilities using probabilities from a continuous random variable.